Hey there, we're going to do our next lesson on implicit differentiation. So everything that we have been working with so far have been explicitly defined functions, which you can see examples of over here on the left at the top of your page. You'll notice that the y, or the f of x, is on one side of the equal sign, and everything in terms of x is on the other side of the equal sign. All right, implicitly defined functions have the x's and y's all mixed together. So you'll see x's and y's both on the same side of the equation, and a constant on the other side in all of these, but you could also have an x on the other side or one of the y's on the other side. Just everything's kind of mixed together. All right. The reason that we want to be able to differentiate implicitly defined functions is because these types of equations do describe curves that are oftentimes not an actual function in the terminology that we usually use the word function for. But also, it allows us to differentiate with respect to other variables. We've pretty much only been differentiating with respect to x so far. And in this unit, we're going to differentiate with respect to time quite a bit. So t, you'll see that here in our first example. And we'll differentiate with respect to, w or x or just anything we want, really. All right, so we are going to start with this implicitly defined function over here on the left. At the top of our first example. And we are being asked to differentiate with respect to t. All right, so we're going to have to apply the chain rule every time we take a derivative. Since none of these terms have a t in it, this all requires the chain rule. And really, even if it had a t, it still requires the chain rule. It's just, you'll see what happens when we try to apply the chain rule when you're differentiating with respect to the same variable. We'll do that on part C down here when we differentiate with respect to x. All right, so that means that every derivative next to it is going to have a d something over dt as part of the derivative. That something on top is going to be the variable you're differentiating on that particular term. All right, so here's how it works. You do the power rule like normal, like we learned in our last unit. So derivative of y cubed is 3y squared. But then we have to multiply this by the derivative of y. And the way we write that, instead of writing y prime, you'll see a lot of textbooks will write it like this, y prime. I don't really like that way because it's not descriptive enough. We want to say that we are differentiating y with respect to t. So we're going to put a dy over dt. We're using Leibniz's notation here instead of Lagrange's notation. All right, so second term, derivative of y squared is 2y, dy over dt. All right, and then the derivative of negative x squared is negative 2x. And then this time we're going to have a dx over dt next to that because we differentiated an x term, so we put an x on top. And then don't forget to differentiate your constant. All right, a lot of people will forget this step and they'll write negative 4 over here, but the derivative of negative 4 is 0. Derivative of any constant is going to be equal to 0. All right, so I encourage you to try part B. It's pretty much the exact same problem, but the variable we're differentiating with respect to is changed from a t to a w now. So pause the video, give that a try on your own, and then come back and see how you did. All right, hopefully you gave this a good try. It's, like I said, it's pretty much identical to the last one. So derivative of y cubed is 3y squared, and then we're going to have a dy over dw. Second term is plus 2y, and we're going to have a dy over dw. Third term is minus 2x, and we're going to have a dx over dw, and it's going to be equal to 0, which is the derivative of negative 4. All right, part C, this is going to, we're now going to differentiate with respect to x, which is what we're going to do in this unit mostly. We'll be differentiating with respect to other variables and later sections. So you'll see how this will change one particular term, and I'll show you that. And then this also allows us to find the actual derivative. That's what we want to do, right? We want to know what the derivative of y is. So we can use some algebra to rearrange our equation and solve for dy over dx. All right, so the first couple terms are going to be another kind of the same thing we were just doing. So we're going to take the derivative of y cubed, which is 3y squared, and we're going to multiply that by dy over dx. Second term, derivative of y squared is 2y. I'm going to multiply that by dy over dx. All right, third term, it's negative 2x. Still apply the power rule. All right, now if we put our chain rule part here, this is what I was kind of alluding to earlier. Well, it would be just dx over dx. All right, then it would be equal to 0. Well, you can kind of think of dx over dx just like a normal fraction, like 2 over 2 or 5 over 5. So anytime you divide something by itself, it cancels out, or better words, it's equal to 1. So when we're doing implicit differentiation, if you're ever differentiating a variable that's the same variable you're differentiating with respect to, then you don't need to worry about the chain rule because it's always going to be a times 1 situation. So I'm going to rewrite this without that dx over dx there. So we have our 3y squared dy over dx. This is a y term with respect to x, so we have to put this. 2y dy over dx, same reasoning. Minus 2x, no need for dx over dx because that's equal to 1, and then the whole thing's equal to 0. All right, so now this allows us to actually solve for dy over dx. So that's what we want to know. That's what we want to find. We want to find the derivative of y. Oftentimes, that's going to be what you need to do. So we need to get the dy over dx by itself. Okay, so there are two of them, which means we're going to have to do some factoring to get 1 instead of 2. And also, there's this term that does not have a dy over dx attached to it. So that's where you want to start, actually. You're going to move that term to the other side. So we have 3y squared dy over dx plus 2y dy over dx. And then we're adding the 2x to the other side, so we get positive 2x there. All right, now we have two terms that have a dy over dx in them, so we can factor that dy over dx out to the front. And that'll leave us with 3y squared plus 2y. Okay, you could have also taken out a y if you wanted to, but that's not really going to be helpful to us. All we're trying to do is get dy over dx by itself, so that's all I'm going to focus on here. Then we just need to divide by the parentheses because we're multiplying dy over dx times that, so cancel it out by dividing, and you end up with 2x over 3y squared plus 2y. And that is your implicit derivative of y with respect to x. All right, so we're going to see some examples on the back of problems just like this one, where we're going to implicitly differentiate the function, then we're going to solve for the dy over dx each time. All right, so find the derivative dy over dx in terms of x and y. Do not leave negative exponents or complex fractions in your answers. Okay, so problem A here, we are going to take the derivative of x squared, which is 2x. Remember, we do not need a dy over dx because it's not a y term. It would be a dx over dx, which is equal to 1. All right, middle term. We have a product of x times y. So we learned in our last unit that when you need to differentiate a product, you have to use the product rule. Okay, I'll write that up here for you again. If you're doing d over dx of u times v, where u and v are both functions of x. Let me try to rewrite those letters so they're a little more clear. There we go. Then that is equal to u prime times v plus u times v prime. All right, so that's what we do here. So I'm going to start with derivative of x is 1 times y plus, and then x times derivative of y. So again, you could write y prime there, but we don't like writing y prime in this unit because we want to be specific about what type of derivative it is. It's a derivative of y with respect to x. So instead of writing y prime, we're going to write dy over dx. Now differentiate y squared, that's 2y, dy over dx. That was a y term, so we have to make sure to include our chain rule part there because that is not equal to 1. And then it's equal to 0. Remember, you're taking the derivative of a constant, so you get 0 in the end. All right, now we're not done yet. We have to find the derivative dy over dx in terms of x and y. So that means get dy over dx by itself. So start with the terms that do not have dy over dx attached to them. The 2x, and this is just a single y. 1 times y is y. So we're going to subtract those both over to the other side. So I have x dy over dx minus 2y dy over dx equals negative 2x minus y. Factor, take out the dy over dx. and divide. And we're done. All right, I would encourage you to go ahead and try B and C on your own. You've kind of seen everything you need to see. They do have some trig in there, obviously, you can see that, but we've learned how to take the derivative of these trig functions, so that shouldn't be too big of an issue. So give it a try on your own and then come back and unpause and see how you did. All right, for letter B, we have the derivative of tangent x, which is secant squared x. That's an x term, so we do not need to worry about the chain rule because it would be dx over dx, which is equal to 1. Derivative of 3x is just 3. Same thing about the chain rule there. And then we have another product. So hopefully you saw that and you did another product rule, just like we learned about, not learned about, but reviewed up here. All right, so derivative of x is 1. I'm not going to write that since it's just a 1. That's multiplied by sine y. And then plus, we keep the x and we take the derivative of sine y, which is cosine y. And then we have to make sure we multiply by dy over dx there because we're doing the chain rule with the y. All right. Okay, that's good there. Now we're trying to get dy over dx by itself. So I'm going to take these two terms that do not have dy over dx and we're going to move those to the other side. I'm also going to write the dy over dx on the left side of the equal sign instead of the right side, just flipping it around because I like it better the way that looks. So x cosine y dy over dx equal to, so we have the secant squared x that was already there. Then we're subtracting 3 and we're subtracting sine y. So I'm going to write minus sine y first, minus 3 second. Doesn't really matter what order you do it in, but I like to have my constant at the end. All right, then divide. Everything's being multiplied here, so you don't have to worry about any factoring or anything like that. Just divide by what you don't want to stay there, which is everything except for the dy over dx. And that should do it. So we have secant squared x minus sine y minus 3 all over x cosine y. All right, you could probably try to do some simplifying there, but it's not really worth it in this case because you still end up with 3 terms, and it would actually look a little messier if we try to do anything else. So once you get your dy over dx by itself, then you're generally going to be good to go. All right, letter C. Hopefully you had time to give this a try as well. All right, so hopefully you noticed this was a product. So you should be, once again, using the product rule. So we take the derivative of cosine x, which is negative sine x, and we keep the sine y. Plus, we keep the cosine x, and we take the derivative of sine y, which is cosine y. And because that's the y term, we have to make sure we multiply by dy over dx. That's going to be equal to 0. Once again, derivative of a constant, even an ugly looking constant like that, when you take the derivative, it goes to 0. All right, a lot of people have a question like, why did I not put a dy over dx on this first term? Well, think about what we were taking the derivative of. We were taking the derivative of the thing that has an x on the inside. So if I did apply the chain rule to that, I would have had to multiply by dx over dx. And we've talked about that, that's equal to 1, so we don't have to write it there. The only time you need to put it is when you were taking the derivative of the thing that has the y on the inside. And that happened over here. All right, so we're going to need to add the sine x sine y to the other side. So we get positive sine x sine y. And then we'll need to divide by cosine x cosine y. Again, everything's multiplied over here, so no factoring required. Just divide by what you don't want to stay there. And you're done. All right, if you got your answer and left it like this, you are perfectly correct. But you may have noticed you could do a pretty simple simplification here using a trig identity. Sine x over cosine x is equal to tangent x. And sine y over cosine y is equal to tangent y. And that does look quite a bit simpler, so I kind of like to do that if possible. But again, not required. You just need to get your dy over dx by itself, and then you're good. All right, have a note here about the TI-89, which we don't use that in our class. We have the TI Inspire, so I'm just going to skip over that. anyway, the like TI-83s and 84s can't do this anyway. Our TI Inspire CXs in our classroom cannot do it either. Only the TI Inspire CAS version can, and the TI-89. So since not all calculators can do this, this always ends up on the non-calculator part because they don't want to write a test question that would be unfair for a person with a different calculator than someone else. All right, so you don't even need to worry about that. This is basically just to check your homework, which you have the answers provided anyway, so we're not going to worry too much about that. All right, this is an example of what a free response question might look like. This is oftentimes on the free response, usually question number 5 or 6. It's not on there every single year, but majority of the time, over 50% of the time, I would say we get an implicit differentiation of some sort. So definitely something that is an important skill that you want to be very, very comfortable with. And so this is our first foray into a FRQ of this type. So we'll practice plenty more of these throughout the year. All right, so let's start by part A is the same instructions we were just doing on our 3 examples up there. Find the derivative, dy over dx, in terms of x and y. So let's apply our implicit differentiation. Product rule, we did that same product rule up there. So it's 1 times y, which is y, plus x dy over dx. Not equal to, but plus derivative of 3y is 3, and we need to make sure to put our dy over dx there. That was a y term we took the derivative of, so it gets the dy over dx minus 10x and is equal to 0. All right, so I have 2 terms that do not have a dy over dx, the y and the negative 10x. I'm going to add 10x over, I'm going to subtract y. Okay, I'm also going to go ahead and do my factoring on this step as well, just to consolidate our work a little bit and make it a little more compact. Okay, so I'm going to take out my dy over dx. That's going to leave me with an x plus 3 in the parentheses. That's from these 2 terms here. And then equal to, I'm adding 10x to the other side. And I'm subtracting y. So last thing to do for part A would be to divide by x plus 3. So I get 10x minus y all over x plus 3. All right, good deal. So part B, evaluate dy over dx at the point 2, 6. So we haven't done a lot with Leibniz's notation yet. So like evaluating at a value when we use Lagrange's notation, like f prime, we would always do like f prime of 2 equals. But with Leibniz's notation, you can't just put a parentheses after. That's not how it's been accepted that we do that. So here's how you do it with Leibniz's notation. Dy over dx, you draw a vertical line. Vertical line means evaluate. And then at the bottom of your vertical line, we're going to put where we're evaluating this. So at the point 2, 6. And we will need both the x and the y because our derivative has both x's and y's in it. Okay, so we'll need both points. Oftentimes when we've done explicit differentiation, we have only needed the x coordinates of that point because our derivative only had x's in it. But now our derivative has x's and y's, so we need both parts of the point. All right, so we're going to plug in 2 for x. That's 10 times 2. I'm going to do this fancy color thing for plugging it in. And then minus, and then y is 6. And that's all divided by x, which is 2 plus 3. All right, so we get 20 minus 6, which is equal to 14. 2 plus 3 is equal to 5. So 14 over 5. All right, part C, write the equation of a tangent line to the curve at the point 2, 6. All right, so we need to know 2 things. To write a tangent line, we need to know a point, which was given to us in the problem, 2, 6. And we need to know a slope, which is what we just found on part B. The derivative evaluated at that point is 14 over 5. So your tangent line would be y minus 6 is equal to 14 over 5 times x minus 2. All right, that's going to do it for implicit differentiation day 1. Hopefully you enjoyed the video, and I will see you for the next one.